Hello, everyone. Yeah, so like we introduced bare metal networking for everyone. Short intro, what we actually try to achieve with, having people here. So I think first of all, network is down, yeah. Of course, as always. Yeah, so we want to demystify, first of all, doing bare metal stuff. So we want you to leave this room with the feeling that cloud is not all that exists here. That, of course, you can always pay someone to do stuff for you, but this is not the only way to go. Then the other part is that networking is not a black magic. Everyone can do networking. Sometimes it's more difficult, sometimes it's easier. You can do it, and you can combine both. So you can do bare metal, and you can do networking, which is needed to do bare metal correctly. And this is all achievable for everyone in here. It's not a black magic. If people working for your favorite cloud provider can do it, you can do it also. So very short intro. So I'm Mateusz. I'm based in Zurich, work at Red Hat. Well, not a surprise. I have background in a lot of different industries, different sizes, so I've basically seen everything everywhere. I've been always doing bare metal. This is why I feel like I'm old enough to tell people that this is not a black magic, that everyone can do it at any stage of their careers. So yeah, cloud, metal. I touched also a bit of network security during my career. That's why I try to combine this, metal, networking, because it always goes together. I don't touch AI. I'm trying not to touch it. I hope if we meet next year, I will not change the song I sing.
Yeah, thank you. So I'm Marcel, based out of Bern. I started actually as a Windows support person and Delphi programmer. Then quickly moved to FOSS and Linux, then realized I need to automate things. That brought me into the cloud. And then I came back more on-prem, especially doing lots of Kubernetes. And because I work at Red Hat, I mostly do OpenShift. And I'm, as part of the services organization, working with customers using OpenShift, and I'm mostly joking, I work with computers, but in a people business, because it's usually talking a lot to people and trying to see how the dynamics between teams are going on, and also how they can work together to actually build something good. And one of the things that I'm seeing more and more being built, and which I'm now also more in, is Kubernetes on-prem. Lots of people in Switzerland do it on vSphere. People are more eager to do it right on the bare metal. And the question is a little bit, why do you want to do it? One of the things is you're championing containers. I mean, you moved away from VMs, you took all your workload out of VMs, you put them into containers. Why do you still need someone orchestrating VMs for you? Sometimes it's specialized workload, either using GPUs or specialized NICs. Sometimes costs of the cloud are a topic, because if people start doing the maths, they might see that a VM running 24/7 in the cloud costs something. Sometimes it's also like you have predictable usage patterns. DHH from 37 Signals made quite some blog posts about how they have predictable workload patterns, they have predictable growth, and for them, they don't need to be able to address exponential growth within the cloud, so they were able to rather build a steady growth on bare metal on-prem. Some people want to do virtualization, maybe only kata containers. Some people might have requirements for confidential containers, meaning starting a container in a VM, but that VM is moved into a secure enclave, and then like memory is encrypted and things like that, which you can do, for example, on Azure, but still, if you are at the point that you don't trust your cluster admins to run certain workload, then why do you trust another corporation to run your workload? So maybe that's one of the things then why you want to have it on-prem. Non-technical requirements, all legal things, data need to be in-house, you need to have a plan when a cloud provider goes away, things like that. Then we have all the specialized edge use cases where it's not anymore about just running embedded systems, it's actually running Kubernetes containers, either, I don't know, out in a warehouse, but also in cell phone towers, or running Kubernetes on a cruise ship that is not connected to the internet while it's cruising around the ocean, and then only coming back when it's back in the harbor. Or you just see that you have lots of clusters, you have lots of demand, and you want to address certain flexibility. You want to segregate more between cluster users, actually because Kubernetes wasn't really built for multi-tenancy, and it especially makes it hard. And that's why when more lightweight clusters are something you might want to do, and for that, for example, you can have one large bare metal cluster and then having your control planes externalized on that bare metal cluster, and then having the worker nodes just as either VMs on that bare metal cluster or as other bare metal hosts within next to it, and so on. Now, if we look at Kubernetes in the cloud, then we actually are consuming quite some resources out of it. So that's just a basic example, but we see we have a public IP, we have load balancers, we have network, we have actually VMs, and we have like a container registry, we have an object storage, and all of that is consumable through an API. And like if you want to start a Kubernetes cluster, we can then use something like Terraform to create all these resources for us. And networking-wise, we create public and private networks. We create DNS records, because without DNS, things are going hard to be discoverable. We add load balancers. We add network segmentation like NSGs or other network firewall rules, and so on. But if you go on-prem, then you start with that. You just start with an empty set of racks, and you need to make a lot of decisions. So you need to choose the right pizza box. Like, is that 128 core server with 4 terabyte of memory the right choice for your one control plane node, and you need 3 of them? And like, really? Or is it? It's probably even too big for worker nodes, depending on the workload you want, and you don't just switch it through API calls, because you order them, you rack them, and so on. The question is also density in terms of if you have virtualized things, the virtualization also gives you a way to put more things on physical hardware without the virtualization layer, and just containers running pure on Kubernetes, defining I need 1 CPU as a request, not as limit, then your 1 core is gone. On a virtualized system, that 1 core might still be shared with other VMs. So like your 1 physical core might also be used otherwise if it's not used within your container. Like there you also need to think about how dense you can pack your bare metals, and then kind of like if they need to flip over in case of high availability, updates and so on, like how much spare capacity do you need to have aside? So that's a lot of questions you need to find answers for, and it might depend on your workload and so on. Another thing where here we see it, there are also barely cables in it, and you also need to think about the network that you get. And we saw that, like, when we talk about networking, we usually also talk about load balancers and IP management and DNS and so on. But what you might end up in a data center is just spine leaf design. Maybe layer 2 even ends at the top of the rack. So how do you have IPs moving around different racks if your layer 2 terminates at the top of the rack? And that's actually the idea of the networking people, that when they give you such a design, they just say, hey, look, we're just a fast fabric that routes packets, and like all the complex stuff, do it upwards. And the next upwards layer, if you're gonna deploy Kubernetes on bare metal, is you. So you need to do a lot of these things there. Additionally, for example, load balancers might not be available, depending on your team and so on. So you will need to solve a lot of these things when you start building bare metal clusters somewhere on-prem. Now, there's a whole stack of layers where packets are flowing through, and Matt is now going to see a little bit like how we do that on one of the lower layers.
Mm-hmm. Yeah, right. So you can see at this slide, it's quite complex. We have a lot of layers. If you don't see, I made it white. Before cluster, it's actually multi-cluster end-to-end networking, because yeah, if you go from the top of this, it starts with gateway API. So it's basically trying to tell you that once you solve all this stuff locally for your cluster, someone will come sooner or later, usually sooner, and will tell you, oh, but now I would like to have a native connectivity between this cluster and some other cluster, and this other cluster runs at the other end of the world, and sometimes it runs in someone else's data center, and those companies are not VPN interconnected, and hey, can you solve this for me? So it can scale out indefinitely. But I actually want to start from the other side. So I'm not sure if you've been to the intro to the CNI talk, but I'm very thankful this talk happened before ours, because basically it gives us for free solution for this, node, OVS, OV, and this is our, our implementation. Guys from Isovalent call it differently, but basically they solve this problem for us. They educated you about the CNI and this layer. So I can spend the remaining time we have here in telling you a bit about this layer, which is ingress controller and platform load balancing. I will not be talking about connecting this with private cloud, public cloud, and all this kind of stuff, because we could spend here hours to talk about all those layers. And the same, we will not be talking anymore, minus this slide here, about connecting cables in a data center, because this is something that can go for ages. Happy to talk about this afterwards, but here we need to time box this. So ingress and load balancing, and I hope then during the questions we can go deeper into stuff. So yeah, so first point here, cluster load balancer, and also disclaimer, what we are showing you here is basically what we learned during some years of selling this framework and designing how to do this stuff on-prem. It's of course opinionated, because whenever you choose to implement a solution or to use a ready to take from the, some product, some component that already exists there, you are always opinionated. There is not a single problem that has only one solution, so we always pick something that we like. in our experience, we always try to take the simplest component that solves the problem that we have, and you will see it in the few next slides, because you can start asking afterwards, hey, but why didn't you use this fancy new shiny technology? And my answer will usually be, well, if there is something simpler that works and solves this problem, I'd rather use the simple thing because I will spend time debugging other things anyway later on. So cluster load balancer, so you already see two product placements, keep alive the HA proxy, so you basically have the answer to how we do this, but some intro to why you even need this. Because, okay, so let's assume for simplicity that we'll be working on a Kubernetes cluster which has only 3 nodes. Why not, It's HA enough, but it's more complex than only 1 node. So then as a user currently in the cloud, what are you used to? You get your kube config, right? It has some API endpoint. You talk to this endpoint, and you don't care what happens underneath, right? So you get one, like api.mydomain.com. It usually goes to one IP address, and you always talk to this, and there is some magic out there that does this stuff for you. But once we go to the data center, you realize, well, there is no any magic. I have basically 3 nodes. So they will have, at least 3 different IP addresses. But I still want to have this kube config with one endpoint, right? So because I don't want to have separate kube config per node and then try to, play round robin or guess me what not, which node works, which doesn't. So you want to have a load balancer. A basic one is enough, which basically means we create one virtual IP that will have those 3 nodes behind, and it serves the purpose, right? Later we'll start talking about the DNS, so this virtual IP will get a fancy domain name, but basically you build what you get from the cloud, plus minus some limitations. So this is what you need to do. You need to create cluster load balancer to access your API, and this is for you as cluster admin. But you have some users, right? They deploy applications, so they want to have basically ingress access for the applications. You very quickly realize it should not be the same address. You should not reuse one for the other, because once you start building more complex cluster, well, do you run API on the same nodes where you run your workload? Well, you should not, you may, but as you grow, you will not be doing this. So we quickly realize that instead of one virtual IP, you get more than one. You start with 2 from the very, very beginning, but it can quickly grow. Still, the same stack that we have here, it will scale. So it doesn't matter if if you start with 2 virtual IPs, if you go to 200, keep alive D and HA proxy, they will still do the job. It's quite hard to beat them on this metric, and you will ask me probably very, very soon, why do we have both? Like, if we have keep alive D, which is responsible for the IP failover itself, why do we need a HA proxy there? Like, I told you about simplicity, and now I introduced 2 components somewhere where I could have only one, right? Isn't it strange? So, well, we start, of course, building it as simple as possible. So I start with keep alive D only, but then I quickly realize, so what experience would I like to get when I talk to the API, and at the same time something breaks with the kube API server in one of the nodes? So do I really want my connection to be terminated, to be reset, when kube API itself reconciles from one node to the other? Well, it would work. I just resend my request. It will work in the second attempt. But is it the elegant way to do it? Well, I'd rather say not, because I'm all the time connecting to the same IP address. So why should I get connection reset? Because something in the background is, switching the path. It's purely cosmetic issue, but I like those things to work nicely. So I decide to put HA proxy behind, because HA proxy will then take care for me for this basically not terminating the connection, because as initially I have keep alive D in front of my kube API, now I'm putting HA proxy in between. So as long as HA proxy is not dying, the IP session will not be terminated. Okay, you could ask me, well, but you are just shifting left the problem. What if HA proxy dies? Well, I can play it back. So what is more prone to fail? What is more complex, HA proxy or kube API server? Well, we go this again, simplicity. From my experience, Kube API server fails and dies much more than HA proxy, which is properly configured and tuned. And this is basically what I wanted to achieve. My end goal was that whenever Kube API proxy dies, Kube API server dies, as long as at least one of them works, I don't want to even notice this at the level of IP session, because why would I? So this simple stack of those two components does the job perfectly. You need to configure health checks in a smart way. This is implementation detail that we can discuss sometime later or not. If you run with the defaults, you will notice that it's not always the optimum, but this is the case with every component you ever use, right? Yeah, one side is quite complex about the installation process itself. I don't want to spend too much time there because I want to show some more fun stuff. You know, maybe we do some live coding, try to break some tools. But basically, what I want you to remember here is that it all works perfectly fine, what I said till now, minus the fact what happens during the installation itself. Because it's super nice to say, oh, I have this stack, it's installed, it works. But then you ask me, well, chicken egg problem, it comes quite quickly because, yeah, where do I install keep alive D and HA proxy if I'm only installing this server right now? So yeah, we designed internally some process which will basically take care of, you know, first having this load balancer on the Bootstrap VM. I'm not sure who's familiar with the process of installing Kubernetes from scratch, in fact. Like, okay, we have one, that's better than nothing. But you get the idea that first you have this Bootstrap VM, so you have this machine from which you install your cluster, then it goes and it starts installing the cluster. The experience I wanted to have is that I will be using my target cluster IP address already to talk to this machine which installs the cluster. Because again, I want to have streamlined experience, which means I always want to talk to this one IP address. I don't want to do installation and then switch my kube config to talk to something else. Well, this is my IP address, my data center. I will be always using this as Kube API. It does that for some period of time. It will be installation API, and afterwards it will be target API. But yeah, let's not spend time here because it's too complex and you will fall asleep because it may be boring. There are always some limitations. Yeah, there is no tool with no limitations. So what happens here with this stack that I told you? Well, scaling to some extent, because with the design, how we use keep alive D and what is the protocol underneath, we will have this IP address only on a single node at a time, which is not a problem unless you start bombarding the API with the requests. So if this is your use case, then of course you can plug some external load balancer. It will take care of this. Like, you know, people buy F5 for millions of bucks, and then they start doing crazy stuff with this. It's doable. There are some hiccups always, because in this topology, it's not so easy to plug F5 for internal cluster traffic, because now imagine you have, you know, 3 nodes in your data center. There's somewhere in this data center we have this F5. You don't really want the traffic between node and node to go through F5, right? That would be nonsense. But, you know, I've seen this happening. People do it. It happens. So I just want to say, be aware of that. So, you know, internal traffic is internal traffic. External traffic is external traffic. And also no isolated L2s. This is once again because of the protocols we are using. So keep alive D is based on ARP packets, VRRP protocol. So it will not cross broadcast domains, which means in a simple setup, you need to take care about your L2 if you want to span it across multiple racks or data centers and so on. It's not a rocket science. Any decent network equipment can do it. But again, it's not something you get by default for free. So be aware, you may hit it sooner or later, but it's easy to solve. And yeah, once you start deploying topologies where you have, for example, workers in a DMZ, finance institutions, they like to do it, you know, because they expose app which runs on a machines physically in a DMZ, then they have control plane in a secure zone. So they have routing between workers and control plane, but not all the workers can talk with other workers and all this stuff. So also be aware, you will start hitting issues because in the perfect world, all the nodes in the cluster would have unlimited connectivity with each other. Because this sounds like a sane configuration, then reality check comes and this is not true. You will notice sometimes, and if someone manages your network infrastructure, you may as well see that you don't get default connectivity between different racks, just because how the infrastructure is configured. Easy to overcome, but be aware once you start debugging stuff, it will pop up sooner or later. Oh man, DNS, yeah. Any DNS experts? Who considers themselves DNS expert? Ah, we have one, okay. So you don't need the next 5 minutes, I guess. Well, no, everyone hits DNS issues at some point. So in our scenario, we are designing these clusters. So what do we want to have nice experience? DNS for API, right? DNS for our applications. That's kind of obvious. We also want to have DNS for internal cluster traffic. This is what I just told you. Because if you start doing load balancer that is visible from outside, you will realize that it's very easy to start mixing traffic. And sooner or later, you realize that some traffic that should have stayed internally, it's talking to the API via external endpoint. That's not nice. So in our design, we just create a separate endpoint for internal API. And we put it behind DNS because we don't like to use IP addresses. We are opinionated, so we are using core DNS, and we deploy it as static pods. Why do we do it? You could say, well, I have my DNS infrastructure already. But to streamline the experience when you start installing a lot of clusters, I don't want to have this process that whenever I start installing the cluster, I go to my network admin and I ask them, hey man, can you create me DNS record for this, for that, for that? He tells me, well, I can do it next sprint or maybe in 5 quarters. Well, I want to do it myself, so I can just deploy it as static pod, and I have my own DNS internally. It works perfectly fine, but you need to remember one thing, and this is, I would say, Docker implementation detail. So how does name resolution work in container world? When you create the container, the runtime that you are using, it will go to etc resolve conf, it will copy it, it will paste it into container. Nice, super nice, all goes well. So I go back to this machine where I deployed core DNS as a static pod. It runs on localhost, super nice, all good. I can talk to 127.0.0.1, I will get responses, right? I go back to my container, bam, I cannot resolve a name. Why? Because 127.0.0.1 inside the container is not 127.0.0.1 in the host, right? So either I do host networking, which is not nice. We don't want everything to use host networking in this world. Or what I'm doing in this scenario, and this is why I mentioned network manager hooks there, I will rewrite inside the container this 127.0.0.1 into node IP of the machine that I have. So basically, that would be, private IP in the data center of this machine. Whatever Linux kernel will take care of this. This traffic will never leave the box, but it will leave the namespace. So this is all I want to achieve. Yeah, it's really hell to debug, because once you start having DNS issues inside a container, you never know, which direction to start debugging. So yeah, just be aware that that happens. Kubelet node IP, I would like to skip this. So basically all I want to say is that kubelet configuration is complicated on its own. And one part that is very, complicated, and you will hit this in your bare metal topologies as soon as you start deploying something more complex than one single IPv4 address, is that you need to tell kubelet which IP address to listen to. And this is important because this is how nodes in the cluster talk to each other. This is how masters talk with masters, workers talk with masters. They talk via kubelet. So kubelet as a process needs to bind somewhere. This somewhere is IP address. You don't want to bind to everywhere. You want to bind to a specific network interface. So it would be as simple as telling kubelet, hey, this is my internal network. Please use that. But not often it's as simple as saying, I have only one internal network, thank you. And you will see that kubelet can be configured in a lot of different ways. So you can basically not provide node IP. You can put 000. You can put IP address. You can put multiple IP addresses, comma separated. you can just say IP stack without saying which IP address. There is a lot of logic internally. The amount of combinations is enormous. Don't try to understand them because it's impossible. And it changes release to release. So yeah, I told you that kubelet needs to live in this subnet where your nodes live. You don't always have that subnet because if you have, for example, worker nodes in a DNS, then you don't have one single subnet between all the nodes. Yeah, it will get complex, and yeah. So also one of the scenario, once you start doing HA at the network interface level and so on, I've seen people having machine with multiple IP addresses in the same L2 subnet. So this is reverse. This is also a problem because then if you don't have smart switch, you will get into the loop which will disconnect you. But even if your switch protects you from doing this stupid stuff, kubelet is not aware of that. For kubelet, this kind of notion of multiple IP addresses, it doesn't really exist. And if you want kubelet to bind to more than one IP address, it's also quite fragile because I basically try to tell kubelet, hey, bind to 192.20 and then to this other address which is IPv6, and I'm using cloud provider external because I was deploying this on the on-prem vSphere, so I wanted to have cloud controller there. And kubelet tells me, oh, well, sorry, dude, but dual stack is not supported when using cloud provider. Well, thank you very much. So I basically did PhD and spent weeks on understanding this table. And when I actually try to run you tell me it's not supported. Well, thank you very much. So yeah, basically, this was the beginning of a disaster with dual stack and IPv6. I thought, oh, it will be super easy. I mean, come on, it's 2024. Dual stack should be something we have by default, right? Well, not always, so yeah. And, it's Kubernetes, it's new technology, it's Golang. I thought, maybe this is problem because it's too young. But then I started working at the level of Linux tools, and I realized they also have these problems. So let me try showing you something. Yeah, I've lost the internet. I will try to quickly recover. But basically, I want to play a game with you and the Golang. So what are we going to do is we will try to guess, or, well, not guess, to recognize IP addresses. Is it IPv4 or is it IPv6? It sounds easy, right? Why would we play something like this? So who feels that they can excel without me showing the examples here? Anyone confident enough? OK, so, maybe I'm not so good at Go. So, I go to Stack Overflow, and I start, reading about how to distinguish IP addresses. And, you have some accepted answer. Yeah, one of them says, oh, Jimmy answer is correct, but complicated. I would simply check IP. We convert to 4, and we check if this is not empty. People accepted, well, 60 people, that's a lot of Stack Overflow. Sounds reasonable, right? And as we start reading deeper, basically people agree with him, and they put more research to the subject. I read what is this function. IPv4 returns, is this one? No. Yeah, 2.4, yeah, that's the one, thank you. If IP is not an IPv4 address, 2.4 returns nil. OK, that should be a good start, right? So what do we get with this one? This is our address, 192.168.1.10. That should be easy, right? Anyone? OK, we get 4. That's easy, come on. Nothing fancy. OK, error handling is not super nice. So let's put trash there. What is going to be the answer now? OK, we have answer IPv6. Let's see. IPv6. OK, so far so good. This is very dumb error handling, but at least we get common understanding, right? We know what we play now. So something like this. V6, OK. No other voice, so OK, V6. Let's do something better. What now? Who's for V4? Who's for V6? What is the prize? V4. Okay, let's hold on for a second. You know, it's Golang. It's only one of the libraries, right? Let's try Python now. So let's play the same game in Python. We have this function IP address something something. So let's use it. Python. Okay, that's easy, right? So far, so good. What do we get now? Anyone changes the answer from the previous one? Okay, well, nice. So let's try to read RFC, what it tells us. Oh, we get this monster which is called IPv6 addresses with embedded IPv4 addresses. Oh boy. And we have this monster, IPv4 mapped IPv6 address. What kind of a name is that? Yeah. And if you want to read more, they tell us go to the next RFC read about this. No, I'm not going to do this. But you know, okay, those are just programming languages. I mean, people make mistakes, right? So that shouldn't be something too serious. So maybe at least at the level of the Linux, they handle stuff properly, right? So we have this tool, netcat, which can open a socket. Okay. So far, so good. No problem, right? Can we break this tool? I mean, it's Linux. It has what, 50 or 500 years already. It should be fragile. Oh boy, invalid argument. What is invalid argument? Come on, come on. It's a correct IP address. We've read RFC, right? Let's S-trace what it does. The last part before the error, invalid argument. Oh, we see it tries to open a socket which is IPv6 socket. So it seems like it followed the Python practice. It recognizes this IP address as IPv6 address, but then bang, kernel doesn't want to open socket like this. Can we fix that? Well, we can, forcing it to use IPv4 socket. Now it works, no error, right? So now you please explain me, you know, who's right in this story here, because I don't know myself. Well, I read RFC and they are complicated and yeah, that's basically, you know, I wanted to show this as an example because people think, oh, there is not much we can do there, invent there. It's all there since forever, so we must have solved all the problems that ever existed there. Well, we don't, and we won't for a long time. So yeah, we could discuss this for ages, but let's not.
Yeah, and maybe just one thing to complement there a little bit is, like you've seen, we talked about keep alive D only be able to, I mean, within the same broadcast domain, but we obviously sometimes need to overcome these limitations. We have solutions for it. We have standard networking protocols that allow us to route things like, and we can even add things to that routing tables. It's a protocol called BGP, and for example, MetalLB has support for it. So easy, let's add BGP on our nodes, and then we just talk with our router, and they just do the routing towards the IP we announces. But now you're not anymore like isolated in your networks, but now you need to go over and talk to the networking team, and they will ask you, you want to do what? You want to you want to inject random IP addresses into our core networking feed? Are you sure? How, like, what will you send us? How do we trust you? And things like that. So, like the issue there is then actually like that you need to establish a common understanding of how you want to do it, but you also need to help them on the other side to understand kind of like what you want to do and why. And like additionally, this integration then brings a lot of more complexity because like keep alive D debugging within the same layer 2, easy, you have all the tools available. But now debugging BGP announcement through the whole core network, you will not be able to do it within your Kubernetes team. You will need some networking experts in it, and that adds a lot of more overhead, makes debugging less easier. It's a nice thing, but it adds the complexity back again. So things to trade off. Question is maybe also to the other team, hey, can we just have an API for it, and then we can just order load balancers from you, and then we can integrate. So that's maybe also then when they might start thinking of offering their services as a product and as consumable through API and not through email and so on. Excellent. That's some of the stuff we thought might be interesting to think about if you start building bare metal. Some things you don't need to, because people like Matt already did the hard part, figuring out how to parse IPv6 and IPv4. Yeah. So that's it for now, and thank you so far, and we're open for questions.
Thanks a lot, Matt and Marcel. So, any questions about RFCs or other topics? Back there, can you pass it on? Thank you.
Yeah, hi, thanks. When you're talking about IPv6 with customers, are they actually interested anyhow? And if you do it, do you actually do dual stack clusters? Or do you just put a load balancer in front of it, run a single stack IPv4 cluster, and let it handle everything in front of it?
It will, of course, depend on the customer, but they definitely do IPv6. I have one customer at hand which does IPv6 because they run out of private IPv4 addresses. So this is some scale, just so you imagine. I mean, you can run the numbers. So there are customers doing IPv6. There are customers doing IPv6 only. There are people doing dual stack. I think this is the most difficult group because they do dual stack because we basically try to force them. So I would say we have customers doing IPv6 because they are very well educated and they do understand they need v6. They don't do any hacks like, load balancer in front of v4 cluster. No. They do native IPv6 on everything. So pods have, global IPv6 addresses. It's very elegant. And of course, majority does old school single stack IPv4. So.
Yeah, we're seeing more people asking, can you support IPv6? And then we say for sure. But, and then you are asking back, okay, can we get networks and so on? And they're like, oh no, we just wanted to know that we then can. And some say we have a concept, but it's not rolled out, maybe next sprint or so. One of the things that I usually see a little bit with IPv6 is where people would like to go, but it's more the surrounding tools that are an issue. And then it's okay to build your stack, but if all the surrounding tools and layers don't support it, then that's usually the reason why there's a lack in interconnectivity to the outside world or so with IPv6.
Over here.
So you've covered networking, but I was wondering which experiences you made regarding storage, high-performance storage, and networking.
So I would assume the answer is easy because from what I'm working with customers, they just have a separate storage network over high-performance NICs. There is no other traffic over this network. So basically, the answer to this question is you build dedicated storage network, and that's it.
Yeah, and this is from where the whole node IP complexity comes from, because you start up booting machines with multiple NICs, and then the question is which NIC to choose. There are ways how you can annotate that and things like that, but this is because you then really want to separate management traffic, so kubelet traffic, from the storage traffic.
And Kubernetes originated in a world where you have only one NIC, because, you know, VM in a GCP, you get one NIC, thank you very much. No one ever thought that people will start using it the way they use. So basically for Kubernetes, the notion of multi-NIC does not exist. Also for Kubernetes, I mean, try getting multi-NIC pod in an elegant way. Well, people hack stuff around, but there is no elegant API. People discuss this upstream, you know, for ages, and it won't be solved for the next 50 years.
And that's maybe actually the thing, when you need to solve it, you just solve it on the Linux level. So you just need to have like your standard Linux routing in place. You put kubelet on top, make sure it only binds on one address, and then it's solved, kind of.